Welcome to the webinar. You have entered as an attendee in listen-only mode.
Okay, Tianzhen, are you ready?
Yes, we are ready.
Okay, so I will do some introduction. Good afternoon, everyone. Or good morning, depends on where you are in the world. So I'm very welcome you to join our webinar series organized by the IBPSA USA Urban Scale Simulations Subcommittee of Research. My name is Bing Dong. I'm a professor from University of Texas, San Antonio, and I'm the co-chair for the Urban Scale Simulation Subcommittee from IBPSA USA. So today, we are very glad to invite Dr. Tianzhen Hong from Lawrence Berkeley National Lab to present his work on the urban scale modeling and simulation. Tianzhen, please go ahead.
Yeah, so I'm Tianzhen, as being just introduced. So I would like first to thank IBPSA USA, especially this Urban Large-Scale Simulation Committee for putting this together. So I will take this opportunity to share with you some of the urban systems research we have been conducting for the last 3 to 5 years. And I also have Yixing Chen and Xuan Luo as my colleague to present some of our work. So we are going to give you like some updates and ongoing research about using building, urban scale building energy modeling to inform cities building energy efficiency, at a large, scale. So the agenda. So I will give a quick overview of the urban modeling, and then Yixing will talk about 2 case studies, using CDBES, and Xuan will talk about how we model urban buildings, considering the interconnection of buildings, using Energy Plus, and Yixing then will give a quick demonstration of CDBES. It's a web application, and so it's freely available on the web for everybody. And last, we have the Q&A section. So while we study, cities, I think we all know that, cities are the hub of our economic and, population growth as well. So it consumes about 70% of the energy. Also emits about 70% of the greenhouse gas emission. And obviously it generates about 80% of the GDP. So I think that's where all of, energy environmental issues, that needs to be, focused and tackled. So our mission is about, is there a way, what kind of technologies and strategies we can put together to improve the city, to cut energy use by, per capita by half, while we still, maintain economic, population growth at the same time improving, resilience and sustainability. So cities, have more and more goals in terms of this. So if we look at the urban research, we are basically talking about very broadly, different sectors or area, if you will, right? Building, this is one of those. This is transportation, land use, air quality, water issues, public health, and electricity grid. All these are connected in one way or the other. So cities is a complex system of systems, research, if you will. So particularly, if we look at the buildings, which, in the U.S., the building sector in cities consume, between 30 to 70% of the, the primary energy. So there's city profiles by this city energy project. And if you look at, for example, a city like San Francisco, all the buildings consume about 52% of the energy. And in New York City, you would imagine the ratio will be higher, it's up to 70%. So I think one of our research focus is to looking at the building stock in cities and looking at, ways to help support cities how to cut their energy use by half, in the building stock. So I mentioned earlier, cities have challenged about all energy and environmental goals. So one, more and more large U.S. cities, are, aiming these, we call it 80 by 50 goals. So basically try to reduce the GHG emission by 80% by 2050. So I think to achieve the goal, what they really need is a lot of, transparency, open data, and tools, to support their effort, to track, to measure, their progress. So we have been, working in an area, try to provide data and tools, and be able to collaborate with cities how they or their consultants, use the tools, to sort of support, prioritize their, for example, retrofit investment, track their progress, like energy consumption emissions in the building sector, try to inform some of their policy making, for example, incentive rebate design, look at the climate change impact. And we've been working with, a broad array of collaborators and partners, cities, urban developers, other DOE's national labs. We also work with NIST, it's a Global City Teams Challenge, and some of the nonprofit organizations like C40, USDN, Smart City Council. There's also International Energy Agency, program in energy in buildings and communities. And of course, universities are very active, so we also work with some universities and an industry as well. So CityBS, as I mentioned before, so it's a web-based application. As you can see, it is. So it's a 3D GIS integrated platform, and under the hook is a CityGML international standard of 3D city models. So, it's an effort how you consolidate cities' building stock data into the CityGML. And so we can visualize the performance of building. You can see all these boxes, each box represents one building, and you can color code the building stock by different metrics. It can be energy use, it can be energy cost, it can be peak demand, it can be savings, it can be, energy star score or compliance status of some local laws, related to building, disclosure. And you can filter the building stock. Particularly depends on what your interest or project. You may want just to look at a subsector of the building stock. So the workflow, basically, we have been designing the architecture of the CityBS. So there's a, if you will, there's a sort of 3 layers. On the top, there's a data layer. So, obviously, under the hook, we are using Energy Plus and Open Studio for the detailed energy modeling. So, it's got weather data, and the building model, of course, it uses a lot of geometry data. The building stock data also includes the building type, floor area, and, the vintage, all those, information. And then use cases, so just illustrate, some of the use cases that our platform can do at the moment. We do portfolio scale energy benchmarking. We're planning to do urban energy planning, and I think currently we have invested a lot of our time and effort in doing this large-scale energy retrofit analysis, and I think we introduced it's one of the case studies. And if we get access to large-scale, smart meter data, we're also interested in looking at some of the building operation, at a large scale. So this is a illustration of how we work with cities at different departments, to collect and integrate their data sources to develop these master building data sets. So, cities have data, in different departments. For example, we have the building footprint, from one department, the land use data, from the planning department. There's also counties, tax assessors records. And the Department of Environment in San Francisco also have their public building energy disclosure, data set. So all these data sets, right, they have different attributes for each building. So how we massage them, integrate them, create this master building data set. So in this case, for San Francisco, so there are about 200,000 buildings, and each building has one record, and we have about like 200 attributes. Of course, some buildings have more, some buildings have less, and so, And then we integrate that into a master database and then standardize the terms, using the Department of Energy's BEES. These are Building Energy Data Exchange Specification. So if you will, basically that's a standardized, data dictionary, right? And then we create the database in different formats. So CityGML is one. We also create one is, GeoJSON and GDB as well. So these different formats, used by different tools for different applications. So talk about this CityGML. So, the development has been going on for about 15 years, and I think the good aspect of CityGML, is big and designed to represent all the city's infrastructure, including buildings, all the transportation, streets, terrain, water bodies, trees, and if you will, everything you see physically in city, they try to represent that. And it provides a flexible way to represent, these are physical objects, in a model. For example, at the bottom of the figure, it shows there's a different levels of detail, they call it LOD, to represent a building, from very simple, like just a footprint, to a simple shoebox, and then to adding more details like the geometry, or floor roofs, the facade, shading, all the way to level 4, and that with detailed internal, partitions, of the space, and that depends on your needs. So these different levels of detail provides flexibility. Especially we're talking about hundreds of thousands of buildings in city. Some of them have more detailed information. Some of them have very limited information. So I think this CityGML provides very critical flexibility for representation. So we have users like from research community. It's also consulting companies, and interesting to know, there's also quite interest from international community. This is just some statistics, but it's about half a year outdated. So when we talk about modern buildings in cities, it can get complicated, from the details of modeling, also from the scale of computing resource. So it can be an exascale computing problem. Exascale basically is we're talking about 1,000 times faster than the current machine we have. So and why is the exascale problem? I think if you look at, well, there's hundreds of thousands of buildings in a city, right? And we need to model these buildings at very fine spatial and temporal resolution, right? And then consider these buildings, they are not isolated. They are not isolated and simple individual. They are connected one way or the other. If you look at a neighbor street in a city, right, buildings on both sides of the city, they have very strong, radiant heat exchange, right? There's a sharing effect. There's also coupling to the local urban microclimate. We're talking about this urban heat island. And if you have some district systems, they're also serving a group building. So they are connected, on that, system level as well. So with all these connections, and then the other connections between buildings and other sectors, we talk about urban microclimate, but it's also potential transportation. So we're talking about electric vehicles. When people arrive using electric vehicle, and they may need to charge the electric vehicle. So it ties to a building's load demand as well as their PV production and how those are used. So considering all these, so it gets quite complicated if we want to capture interconnections between buildings, between building and urban climate, and between buildings and transportation. So there's a lot of computing and complexity. And I think going to the future, the grid also gets dynamic. The building stock will change, the population growth. So all these added together, can basically make the computing as an exascale, problem. And actually, we are working with Argonne, Oak Ridge, and Unreal and PNL. This is an exascale computing project. We call it multi-scale coupled urban system. And in this project, basically, we are very interested in looking into how we develop tools and data to simulate, the interconnections between, the sectors I talk about, buildings, urban microclimate, and transportation. And on top of that is all the pricing and how people make decisions. So if you look at all these, then it's complicated. So we're just in the middle of this 3-year project. I think later Xian will talk more about the technical progress. So now I will pass to Yixing to talk about two case studies using CDBS.
So these two case studies, one is for the large scale building energy retrofit, and the other one we try to understand if we modeling the geometry differently in this urban scale, how is the impact results. So those two studies have been published in Applied Energy recently. So for the retrofit analysis, we picked the 940 office and retail buildings in Northeast San Francisco as a starting point. So if you can see, we pick about like a dozen retrofit measures. So from lighting systems to HVAC systems and water heaters. So you can see from the bottom, from energy CDBS analysis, you can see the retrofit total energy savings as well as the payback year. So for example, for San Francisco climate, upgrade LED lightings, using plug load controller, or using the occupancy sensors and daylighting sensors, and as well as reset temperatures, has huge energy savings, and with low payback years. And also, at economizer, airside economizer also is beneficial in San Francisco due to the mild climate. So also have a low payback year. So these 6 measures seems very good for San Francisco climate, and so we did another packages for those 6 measures, and it's those consider because different measures may have an interaction between each other. For example, in this case, the occupancy sensors and daylighting sensors both will impact the lighting control, and their combined effect may not be the simple sum up. So that's why we do these packages to see all the overall energy savings. So you can see for all those buildings, the saving can be around 30% to up to 50% for all the buildings. And the average payback year is around 4.3 years. And if we models all the 10 measures together, you will see that they have a slightly large savings from like 35 maybe into the 55%, but the payback year is much longer. This is typically due to the climate zone of San Francisco, and the measures may be different for other climate zones. And you can see that from the CDBS extension cells, we can visualize those results. For example, this is the payback year, and then you can see color coding and targeting those buildings. And in here, I will introduce some of the details about how we model the buildings. So this is some algorithm we developed to simplify the staging. So for example, in Energy Plus, we model the buildings in the center. That is the Energy Plus models there, and we need to consider the stagings from all the surrounding buildings. So there are some algorithms because all the surveys are very complex. We use those GIS footprint to create those services and buildings, and those GIS data is very have a lot of noise. So we need to simplify those staging surveys. For example, the first step we do is to simplify those buildings that is far away into rectangular box. So that is and representing their shapes. And the more advanced algorithm we developed recently is to first pre-scan all those surveys and make sure some of the surveys will never impact the building. So we remove all the surveys, and it results much lower, much less surface for Energy Plus to simulate. You will see most of the building will be represented only using 2 surfaces, or some of building can use 1 surface to represent the building. And this can speed up the simulation up to 30 times. And in order to consider the zoning of the buildings, because if we models the buildings in just one single zone, there may some of the cancellation of the heating and cooling loads. So in order to avoid this, we developed these pixel-based automatic thermal zoning algorithms, and that if you have any polygon or building footprint, then we can separate the internal and external zones the core zones and perimeter zones, and for example from the starting point, and then we find all the boundaries and then connect the thermal zones. So you can see on the top is demonstration of the 4 steps of one building, and on the bottom the methods are applied to, for example, this is 4 example buildings, and you can see the algorithm is working very well to processing any kind of buildings. For example, on the bottom first one, you can see a lot of those coordinates is not very clear, and then we can still keep processing all those shapes. And the second studies we working on is to consider the impact of different geometry modeling methods. So in this case, we compare 3 different geometry modeling methods. One is just to models. We still model every floor, but for each floor, we just use one zone. So there is no detailed zoning in the floor level. In the second method, we split the footprint into core zones and perimeter zones. So as you can see here, and also we detect whether there is any attached to the other surrounding buildings. For example, in both one zone and outer zone case, you can see the surface in the right hand side is there is no windows there because it's attached to another building. And the third method we use is called prototype method. And in prototype method, basically we use DOE's prototype building for office to model the building. And in this case, it's a rectangular box, and then we also calculated the orientation from the original building. And then, but you can see there are some place that is no so similar to the original building. For example, the windows in the right hand side is still there because there are more than 50% of the wall has windows in that phase. So in this case, we also study the floor multiplier. So if we use floor multiplier, basically we only model three floors: the top floor and the ground floor, and also a middle floor with a floor multiplier. In this case, this is a 6-story buildings. So the floor multiplier is 4 for the middle floors. And the results we showed here, quickly go through. More detailed results can refer to the paper. And for using the floor multiplier, basically the electricity and the source energy use is different within like 2.5%. So you can see that they are very close. And of course, there are some outliers there. But overall, is 2.5 in the 95 percentile. And the medium is close to 0, you can see. So in this case, using floor multiplier can speed up the simulation for 2 to 3 times. And in this case, we consider the overall portfolio because a lot of building is not suitable for using floor multiplier if they are less than 3 floors, less or equal to 3 floors. So those are considered all the simulation time. It can speed up 2 to 3 times, and with a very slightly accurate comparison. And when we compare the one zone with the outer zone methods, the result shows is agree with our assumptions that if you model one zone for the whole space, and then sometimes when the core zones need cooling and the perimeter zone need heating, then those cooling and heating loads will be cancelled out, and that results in when you model one zone only, we have a less space cooling loads, also less space heating loads, and this contribute to the cooling capacity and heating capacity of the equipment. So, but in terms of the source energy use, for the cold and hot climate that we show the using one zone, we underestimate the energy consumption. But for San Francisco, they seem the climate is mild, so the case is more complicated. And detailed results, we have a very detailed analysis of why San Francisco is showing those kind of increased or reduced results in the case. Because in this modeling, we not only we don't take the cooling and heating load directly and then apply a COP or efficiency value. We model the detailed HVAC systems. And for using the one zone, you can speed up the simulation by about twice or 2.4 times. And then the other way comparison between the prototype methods and auto-zone methods. As you can see on the right-hand side, top right-hand side, the auto-zone, as we mentioned, auto-zone method and the prototype method have some difference in terms of the footprint area is the same, the area is the same, the building area is the same, but for example, the wall area and the windows area are not the same. And you can see from the graphic, the exterior wall area difference. Some of them may be extreme. There are a lot of outlier there, but the average is a lot of building is the same, but also a lot of building is outlier. So that leading to quite large difference in terms of source energy use as well as the equipment, the capacity and loads. So as you can see, the source energy difference is between minus 12% to 19%. And using the prototype buildings can save slightly times, like 1.4 times faster than the auto-zone method, because auto-zone method may create more than 5 zones. For using the prototype buildings, we use every floor is split into 5 zones, 1 core zones and 4 parameter zones only. So it's but using auto-zone, it can create more zones than the prototype. So those are the studies. Then Shen will continue to work on.
Yeah. Next, Shen will talk about how we model the urban buildings interconnection using Energy Plus.
Thanks, Yixing, for a detailed introduction of the techniques and tools. So with the previous mentioned techniques and tools, the traditional building energy modeling can be both improved and scaled up from individual buildings to district and the entire cities. However, this requires a more detailed simulation engine to involve and incorporate this level of simulation. So in order to expand the capability of Energy Plus to model the urban buildings, we added 2 features to enable this in Energy Plus 8.8, which was released last year at September. So the first is we explicitly consider the long-wave radiation exchange between. And previous research reveals an average of 10% difference in cooling load with and without modeling this effect in dense urban areas with high-rise buildings. And as the last figure shows, previously in Energy Plus, the heat balance equations is oversimplified. But to model this radiant heat exchange effect, we added the feature to consider not only the long-wave radiation from sky and ground, but also from its surrounding surfaces, and to model the thermal interaction between buildings. And the other feature we added is to explicitly consider the urban climate model conditions, including local weather conditions, to consider urban heat island effect and urban canyon effect. So we enable this by adding external local air nodes which contain environmental variables to model the interaction among building energy models and urban atmosphere. So this kind of enhancement does not only serve our urban energy model work, but also serves as the basis of another project that Kendra mentioned, urban multi-scale coupled urban system. So as this framework shows, cities are integrated with many infrastructures and human systems, including transportation, buildings, socioeconomics, and energy. So these models are modeled individually previously, but in order to optimize the city design and the operation, we also need to understand the interaction between systems. So the project is to develop a modeling framework of the metropolitan system of energies and economic activities. And the baseline problem is to simulate this kind of coupling within the city block. And our target is to scale up to a city, so that's why it's an exascale problem. This kind of simulation does not only require the enhancement of the simulation engine itself, but also we need to, it requires the common data exchange mechanism to support the diverse content, volumes, and characters of the data between models. It also requires the method to support optimizing spatial and temporal resolution for significant difference in runtime. For example, for energy plus, the runtime is like 2-minute interval resolution, but for urban microclimate, it could be like milliseconds. So we designed the coupled architecture as the diagram below shows, with each model taking different external data sources and integrated them into the common platform. For example, at the upper right, Energy Plus takes building energy, building information and GIS information, and we run 2 levels of coupling. The first is with urban atmosphere with the next 5,000 model, with which we exchange the environmental data. And the second level is to exchange hourly locations of the individual agent data with in the forward, in the workflow, so the live sensor data, historical data, and data from current simulations serves as the input data for initialization output. The data hub shown here holds the data exchange protocols between models. And as those 4 models mostly run asynchronously, the hub also serves to synchronize the models with concept variable change and share data status checks, as well as supporting intensive I/O at every time step. So specifically, take the workflow of the urban energy model coupling strategy with urban atmosphere as an example. So as the diagram shows, Energy Plus allows data input as arbitrary coordinates as a local climate condition from the urban atmosphere model. And it also allows data output at surface zone node level as boundary conditions for the urban atmosphere model. The data exchange is performed as the surface zone and air node levels. At every time step, Energy Plus takes input from the urban canopy, including local air, dry and wet bomb temperature, and in the same time, at each time step, it outputs heat flux rate, zone airflow rate, and also systemic salt flow rate to the urban canopy. And this kind of coupling is manipulated by the air nodes. The node has absolute coordinates with holding those environmental variables and serves as the unit of data exchange. More specifically, this is a case study we are doing right now to study the Energy Plus and 5,000 couple simulation. The baseline model of a city block in the North Branch area of the city. We are testing it within this building block, choosing 5 air nodes at arbitrary coordinates. Some are over the river and
Hello, Xuan.
Hello?
Yes, we are very difficult to hear you. Your voice is fading and fade out. Can you get in close to microphone?
Oh, right. Okay. How about now?
Now it's better. Yes.
Okay. So each surface. So we choose 15 air nodes at arbitrary coordinates. Some are over the river and some are between the urban canyons. And each surface and each zone of each building is mapped to its nearest local air node. So during the coupling, Energy Plus wants velocity and temperature from the urban canopy model, and the 95000 as the atmosphere model wants heat and mass flux from Energy Plus. So based on this architecture, we performed one-way data exchange to analysis the data sensitivity. And we're in the progress of trying advanced coupling architecture to perform the real-time coupling, and it will be our ongoing progress in the future. So let's get back to Yixing for the demonstration.
So next, Yixing will give a quick demonstration of the tool. So before that, I also mentioned, I think at the beginning I mentioned these are some of the research we are conducting. But at the Berkeley lab, we have other teams working on different research areas related to cities. For example, Michael Weller, is leading a team working on numerical tools to model district, heating and cooling systems. Paul Matthews is leading a team working on data tools, to help cities and states, host their building energy data. So the tools include building performance database, B's and C's.
Okay, so the tool currently is hosting, and then you can go to using it. So it's called cbes.build.gov. So if you go to the website, you will see an overview. So basically, those are introduced by Tianzhen already, and the workflows as well. So we have a self-publication here, and then I will go through the steps. So in here we have a simple registration steps. So for example, you can log in or you can sign up, and then there is a place you can go to create an account, and simply we only simply ask a name and email address. So those are be used to associate with your account with the local data set that you created. So for example, in this case, we are using Tianzhen's account. So in this case, you will have like a shared data set that is shared among the users. And then you can also have your local data set if you don't want to share with other people. And then you can manage the local data set. So in this case, we can select one of the case study we just present. This is including about 9,000 buildings in northeast San Francisco. So you can see the platform is very fast. You can loading the data in seconds, a few seconds, and then pop up the data. So there's a features that you can. This is a GIS integrated platform. So you can choose different maps to show the data, and in the left-hand side there are some of the functions where you can filter the buildings based on the building type. You can choose only office building or retails, and then you can select different year of build, if the build filter by buildings and total floor area, as well as any start score and any use. So those allows you to pick the target buildings you are looking at, and then there is a function for you to show the results. So this is the feature of this is more like this page is a visualization functions to visualize the results, analyze the results. For example, this including the baseline simulated results as well as the results for each retrofit package we just simulated. And then it also includes the major data set. For example, this includes the major data set for 2005, and then there are site EUI, source EUI, CO2 emission, and any start score and benchmark statics. So this has include all the real major results for those buildings. And so this is a visualization platform, and then I will introduce the different features one by one. So for the first one is benchmarking features. So DOE created a database called Building Performance Database, which currently includes about 1 million data in the data set. So for these features, we try to compare the buildings we have and the buildings data we have with those the buildings in the data set. So for example, in this case, we compare about 350 buildings in CBES with about 63,000 buildings all across the U.S. These are all office buildings. So you can see for San Francisco, the energy consumption is slightly lower compared to the all U.S. buildings because one reason is San Francisco have gone through a bunch of retrofits and the building energy consumption is significantly reduced. And the other reason is San Francisco has a mild climate. So, but these features provide some of the compared regions. You can compare to a few dozen buildings in the data set. So this is going to assess the building performance database on real time. The other features, all the key features we provide right now is the retrofit scenario analysis. So the usage is very simple. We have about 82 measures in the packages. So for example, you can select from the drop-down list. There is a dozen categories here, including lighting, HVAC systems, plug flow, surface hot water, and envelope systems. So you can pick from there, and then each of the category will have several different measures, including different technologies. For example, for lighting, you can do PA, T5, or LED. And for adding economizer or economizer maintenance, and also plug loads, controls, and so on. So HVAC, windows operations, and then, for example, the heating, cooling systems, you have different HVAC system types. For example, single zone, package rooftop units, and then chiller systems. And under the hood, you can update the efficiency values for each of those measures. For example, you can update the cost data if you have more details. So we provide those cost data based on our CBES project, and then those can be customized. And we are currently also working on a feature to calculate the GHG emission reduction and the material GHG emissions. And also you can customize the efficiency value of the retrofit upgrade. For example, if you say upgrade lightings with LED, then what is the lighting power density end up with the upgrade case. So those are customizable, and also you can add or editing the incentive or rebates if the city provide incentive for those different measures. And we provided 4 different types of incentive or measures. One is based on savings, so it can based on the savings of electricity or natural gas, and it can based on the applications. So per application, you can provide a certain amount of dollars, and you can based on the program, the tax exemption, and also you can based on the interest savings. So if you can provide the financing support with lower interest rate than compared to market, so those can be added, and then the detailed incentive and rebates will be assigned to each of the measures associated with that. So when the measure is finished, you can show up in this finished tab, and the results can be visualized in these district buildings. For example, in here we can pick up one of the magnitude packages. This will be the lighting upgrade, and then we can see all the site energy savings. You can visualize a bunch of different metrics, including the energy use as well as the cost data and payback year, for example. And also there is functions to show you all the savings for all the buildings. For example, if we say all the ECM packages, you will show the savings. For example, this is the 7 packages we created, and then you say shows you what is the savings for each one, and this is the payback year. So some of payback year is 5 or 3, and then if you choose another matrix, they will show you the different savings for. So this case is the savings. I think the first one is LED, and then they are coupled by different building types. So if you say I'm only looking at the office buildings, then you can just hide the others and then go to just look at the office building. So those are the features we provided for retrofits. And then currently we also be able to calculate the energy, the photovoltaic potential of the roof. So for example, you can specify from the manufacturer's specification of the PV modules. You can provide a bunch of input parameters based on that, and then those are the PV cells, and then you can specify percentage of the available roof area, and then the orientation and tail angles. So in this case, we will create a model for all the buildings in the data set, and then calculate the PV potential. So for example, if you go back to these 3 buildings, you can pick the PV potentials there, and then you will show you the generate the PV intensities of on the roof. So we are still working on these 3 energy features, and then if you have questions, you can always. So those are the 3D GIS. You can zoom in, zoom out. Those features are optimized many times, so it's much faster than some of the tools.
Click one building.
And then there is a home buttons here. You can zoom into the building. So if you click one button, you will see the detailed information of each building, including their basic information, and as well as for example, the major data for each year, if they have, and then the PV potential, water consumption, as well as the baseline results and the retrofit scenario of the savings and the cost of savings. And those are just now I present the different methods of modeling. Those are all available through the settings in the simulation setting page. For example, the zoning method, you can choose core zones, perimeter zones, or you can choose 1 zone per floor or floor type building. And then for the top building, you can see whether you are going to use floor multiplier or not, and you can choose whether to model the shading buildings or not. And those for research purpose, if you like to explore the difference. And then you can create the detailed load profiles, already load profiles for all the simulation results, and then you can customize the utility rates. So all the results will be available for download in the CSV format, so including retrofit results for each building, as well as those hourly load profile results. If you check to generate the hourly load profiles, that will be available for download. So in the CSV format to support other visualization or integration. Yeah, and then there's the team.
Good, thanks, Yixing. So I think so that's a quick demonstration of the tool. Maybe we come to this Q&A section.
Okay, thank you, Tianzhen. We have 10 minutes left. So if you, let me see. If you open on your GoToWebinar control panel, there's questions.
Which one?
Something so.
This one?
Yeah.
Okay.
So there's a few questions.
Mm-hmm.
I think I ask people 2 types of questions there because we have a large audience. So
Okay.
So you need to scroll up and scroll down properly.
okay, actually I can read the question for you.
With a question, yeah, need to figure it out.
Yeah, so everyone can help. Okay. So first question is, how do you consider urban heat island effects into urban level energy simulation?
Yeah, I think that's a very good question. So I mentioned we have another researcher, Roland Levinson. So his expertise is modeling urban heat island, effect. And so I think there's various ways. If you have major data, I think currently, right, there's very, many more local weather stations. So you can use those, weather data. I think the other is, as I mentioned, there are also tools to model the urban microclimate, like like 5,000, WAF, and so those tools and can also simulate, if you will, the local climate, conditions. And when we do the energy modeling, we can use those, local weather conditions.
Okay. So next question is, have you compared your larger systems using AutoZone single zone to feedback survey data for the same region or to utility data?
Jim?
So yeah, I think the comparison of the results, we did do a quick comparison. We haven't done the automatic calibration yet, but the results is quite, on average, it is very close. But there is a large difference in terms of the shapes. So for example, for the simulated results, the range of all the buildings, the source energy, the site energy use intensity is around like 100 to 300, but for the real major data is around like 20 to about 1,000. So there is still a large difference between the majors and the simulated. But for different zooming methods, we see the overall total energy consumption is actually quite close. But in terms of the equipment capacity and it's quite different.
Okay, so Tianchen, just to let you know, I have a bunch of questions, so I prefer the answer will be short.
Sure.
Okay, so next question is, how do you actually apply the EEM to the model?
The energy conservation measures, right? So
Yes.
yeah, first we create a baseline model, and then apply all those ECMs individually or as a package. So under the hook, we create one energy plus model for each ECM or each ECM packages.
Okay, and can we use this model to model other cities in the U.S.?
Yes, so the architecture is set up to do it for any location, but I think we will need to develop, for example, the city GML data set for the building stock in that particular city first.
Okay, so this question is not, so the question is, can I ask if the new version of Enterprise you have the feature of trees like the waterfall?
The Energy Plus, Energy Plus.
The new version of Enterprise, yeah, have the feature of trees.
I think in Energy Plus, so trees is modeled like a shading object. There's ways to characterize its geometry in some way of like simplified fashion, and those then can consider the shading. But I don't think Energy Plus consider, for example, the other heat and moisture transport process, regarding trees.
Okay, so next one is, thank you. Are you considering to add district heating cooling system into the tool?
Yes, working on that feature. I think Yixing mentioned.
Okay, so next question is, we are from Brazil, and we would like to know if we can upload a GIS file from Brazil to the platform.
Yeah, so I think we're actually working on some international countries like China and Chile to develop their local data sets. So we develop like a user documentation, detailed step by step how we develop the data set that can be used with city BES.
Okay. So next one is, what have been done about coupled radiant effect between buildings? Are you still implemented it on Enterprise?
The feature is implemented already in Energy Plus. I think Sean mentioned we are doing a case study, a simulation case study. But in the future, we would like to do also the measurement to verify, this kind of radiant, effect.
Okay. Next question is, how did you validate the retrofitting analysis?
Yeah, a good question. I think theoretically, or the best way is, you do the retrofit analysis, you follow up with some real demonstration project, do the MMVs, and verify your model. But I think some of the consulting companies are doing it. We actually just submitted one proposal with this company called Lucia Design Group, and that one of the scope of the proposal is to do like MMV of the retrofit savings.
Okay. Next question is, does city BES have default assumptions to use in locations that lack citywide energy benchmarking data? For example, can it work with only parcels or buildings footprints?
Yeah, there's a way, I think, to down select buildings. I think Yixing shows the filter feature. So you can select, buildings in the city block or certain type, and then, compare with other buildings, in the building performance database.
Yeah. So for buildings, we need to know some of the high-level information added. For example, the building type, the height of the building, right? The number of stories, and their footprint, as well as the year of build. So those are high-level information we need. And then for the US-wide climate zones, we all can model.
Yeah, so I think for this benchmarking feature, basically we are calling the the BPD's API, and it's a free tool, and I think they have documentations on the API. If people are interested, I think can check it out.
Okay. How are you modeling electrical demand and generation?
So the demand basically is based on the energy plus model for buildings. And I think the generation, currently we only model the PVs, on the rooftop. So in the future we may, look at a CHP or some other type of local generation system.
Okay. The next question is about the contact. The site says contact development team to do anything. Does this cost, or are external companies able to get access?
Yeah, so the tool, I mean, if you use the web application, it's free. You just register an account. But I think if you realize, some people, I think, register. So currently we are sort of, development phase, and so it's not a production environment yet. It means that, if you want to simulate hundreds of thousands of buildings using our server, right, that requires significant computing resource. And so, if you're interested in trying out, please let us know. We would love to support you, to use CDBS. I guess the second part of the question is, so we have been sort out a plan how we sort of make a CDBS, available to the broader community, in terms of like maybe web APIs, and so we are definitely thinking about that. But currently the tool is provided as a web application, and if you send us a message, telling us what's your use case, we would open up some computing resource and support your use.
Okay, I think the same person asked the same question. Follow-up question is, it does not let me simulate anything at all, even after signing in. So
yes. So I think I just mentioned, because currently we're hosting this on a server with only 64 cores, so it's a limited capacity. So if you write us an email telling us a little bit like your use case, and we can open it up. Basically, each user has some permissions, like whether you can create your local data set, whether you can run simulation in different factions. So please follow up with us.
Okay. Please follow up with Tianzhen. And last question, does the simulation include actual occupancy and equipment usage, or it is generalized based on square footage of the building?
Yeah, so that's a good question. So I think currently, right, the model is generated using the, for example, if a building in California, we have our local building code called Title 24. So, those would have, like different vintage of code, different efficiency labels, like, like what type of window, what type of HVAC system, their efficiency. And if it's outside California, we're using the default assumptions from the ASHRAE standard 90.1. But if you have better information, so that's another feature we are working on, Yixing mentioned, then you can enter those information, and then those information like detailed system efficiency and configuration will be used in the energy modeling.
Okay, great. I think time is up, and thank you so much, Tianzhen. And thanks for everyone who attended this webinar. And we are looking for the next one. This is our first webinar series of the urban scale simulation. Thank you all. Thank you, Tianzhen, again. Bye.
Thanks, Bing, and thanks for everyone.
Thanks.